So far, we've talked about what are the three factors that determine whether a reaction is even going to happen or not. And then we also talked about the four things that affect how fast or slow the reaction is going to go. And now today we're going to actually talk about how you can determine how fast the reaction is going. So just like when you drive down the road, you can measure the speed of the car in miles per hour. Okay, the way that you determine the rate, the way that you measure the speed or the rate of a reaction is by taking the concentration, the molarity, and also, like driving down the road, you talk about how the concentration changes over time. So it's a measure of concentration, again, in molarity, over the time. So you can say that the concentration of the reactant is going down by, 0.125 molar per second. Or maybe 0.125 molar per hour. It doesn't have to be seconds. It could be minutes. It could be any unit of time that there is. Now, one of the ways that we find the rate of a reaction is we use what's called a rate law. And a rate law, or the rate law equation, is an equation that we use that, again, tells us how fast the reaction is going. So let's say we have this reaction right here. Okay, and that reaction is, and again, the rates, let me back up here just a second. When you calculate the rate, so this rate right here, the speed, in a rate law, you're determining what's called the initial rate of a reaction. And we'll talk about this more a little bit later on. But basically, the concentration, let's say the concentration's right here, initially, because there's a lot of that reactant, it'll drop pretty quickly. But then it does start to level out. And usually, the concentration drops in a curve like that, where initially it drops pretty quickly, but as more and more of that reactant gets used up, the reaction starts to slow down. So when we're calculating this rate here, we're calculating the rate right at the beginning. As soon as that reaction begins, what we refer to as the initial rate of the reaction. So when we write a rate law, there's a couple things that you need to notice here, that the rate, or the speed, is equal to this lowercase k, which is called the rate constant. You can see that here, k, which is called the rate constant, and we'll talk about that a little bit more, times, and we've already talked about this, the concentration, remember those square brackets? The concentration of each reactant. So notice the products are not in there. There's no products in there. Think about that. At the beginning of the reaction, there are no products. So how can you use the concentration of the products at the beginning of the reaction? You don't. So you only use reactants when you're calculating this rate using a rate law. So you take the concentration of each reactant and then you raise it to a power. Now notice that the powers are not tied to the coefficients. Notice it doesn't say 2, 1, 3. It says x, y, and z. Okay, that x, y, and z represents what's called the order of each reactant, which we'll talk about here in just a second. Okay, so a rate law is written by writing rate is equal to k, the rate constant, times the concentration of each reactant raised to a certain power. And if there's only one reactant, well, then it's just the concentration of whatever that reactant is raised to the power of its order. Okay, and when you add up, the order of the overall chemical reaction is the sum of the individual orders. Okay, and we'll talk about what that means here in just a minute as well. But basically, you add up these numbers. Let's say it was 1, 1, and 2. Then the overall order of that reaction would be a fourth order reaction, because 1 plus 1 plus 2, that's all that means. Okay, now let's kind of get rid of that stuff here. So let's talk about these numbers up in the corner, what we call the order of each reactant. Okay, again, notice I did not use the coefficients from the balance equation because you can't, okay? It's not possible. Notice that very next paragraph. It is not possible to determine anything about the order of a reaction from the stoichiometry of the balanced equation. Okay, that 2 and the 3 from the balanced equation do not appear in the rate law equation. The order of the reactants must be determined experimentally or using data from an experiment. So typically you'll be given a data table that shows different trials of the same experiment by changing the concentrations and then how that rate changes. Okay, to determine the order of each reactant, you choose one reactant and compare how the concentration changes from one trial to the next versus how the rate changes at the same time. Okay? For example, if the concentration of the reactant in the question doubles, and so does the rate, then that reactant is first order. Okay, and I'll show you an example here in just a second. This is just to kind of get the information out there. If the concentration doubles and the rate doesn't change at all, then the reactant is zero order. And if the rate doubles and the concentration goes up by a factor of 4, then that reactant is second order. Let's see some examples of that, because I'm sure that did not give you enough information there. So for a reaction between A2 and B2 to produce AB, in the balanced equation below, 4 different trials were run at 298, and there's data collected in the table. Okay, and then part A says determine the order with respect to each reactant. Okay, so notice, and so here's how we would do this. We would say in trials 1 and 2, the concentration, I'm looking right here, the concentration of A2 doubled. So that means it went up by a factor of 2. Okay, and so what we're doing is we're comparing the change in the concentration to the change in the rate. Okay, now for this to work though, notice that B2 doesn't change, and that's really helpful for right now when the other one stays the same. If the other one changes, it's a whole big mess that we'll talk about later. Okay, but for right now, so the concentration of A2 doubles, the rate also in those same 2 experiments also doubles. So the order is 2 raised to what power equals 2? And the answer is, of course, 1. 2 to the first power is 1. So the order is always look at what the concentration does, look at what the rate does, and then raise to what power gets you to get those 2 sides to equal each other. Okay? So therefore, I'm going to say A2, not AS, A2 is first order. And then I'm going to explain what I just said. Because in trials 1 and 2, the concentration of A2 doubles, concentration of B2 remains the same, and the rate also doubles. Okay, and if you say that, the grader knows that you know what you're talking about. Okay, now let's look at B2. Okay, and again, we want to try to find 2 experiments where A2 stays the same, but B2 changes. Okay, so in this case, I'm going to look at trial 1 and trial 3 because A2 stays the same and B2 changes. Now, what does B2 do? B2 goes down by half. And what does the rate do? The rate also goes down by half. So 1/2 to what power equals 1/2? Also 1. Okay, so we can say that B2, basically I can just, that same thing, is first order because in trials 1 and 3, A2 stays the same, and that's important to say that because if A2 changes, then that again, that's going to affect the rate because we know it's first order. And then we can say B2 goes down by 1/2, and again, I would obviously write that out. And the rate goes down by 1/2. So therefore, it's first order. Okay? So order. And then it says, write the overall rate law for the reaction. So we know that the skeleton way to write a rate law is to write the rate is equal to the rate constant, which we'll get into more detail here in a minute, times the concentration of A2 raised to the power of its order. What did we say A was? First order. So you don't actually have to put the 1, but if you don't put anything there, we know that it's 1 times the concentration of B2. Okay, and again, that was also first order, so that is absolutely our rate law. Wait, is it always first order? No, it's not. Okay, many times, again, you'll see. I'm just trying to do an easy one to start. Determine the overall reaction order. Well, first order and first order. This is a second order reaction overall. And again, here I explain all of what I just talked about. And that's all of the answers as well. Okay, and again, what happens when the concentration of a reactant changes, though, and the rate doesn't change? Well, then then you could say, okay, the concentration doubled. So again, here's our concentration. Our concentration is going up by a factor of 2. It's doubling, but the rate is staying the same, which means it's changing by a factor of 1, which means it's not changing. So 2 raised to what power equals 1? Anytime you raise any number to the power of 0, it always equals 1. So therefore, if the concentration changes, let's say we come back up here, let's look at A again. If A doubles, B stays the same, and then the rate also stayed at 1, it means that A doesn't affect how fast the reaction goes. Okay, it means that you can change this concentration all you want. Clearly, the rate is not going to change. And therefore, that means that A is 0 order. And if something is 0 order, you don't put a 0 up here. What you do is you take it out. Okay, if A were 0 order, then it would just be rate equals K. And then let's move this over here. Times the concentration of B2. If A were 0 order. If it's 0 order, you take it out of the rate law. Obviously, in this experiment, it was not. So let's leave that correct. Okay, so again, we say that the reactant has no effect on the rate. The order is equal to 0, and it doesn't make the reaction go any faster or slower. And also, since any number raised to the power of 0 is equal to 1, again, you have to remove it from the rate law. Okay, so when a reactant is 0 order, you see it not affecting the rate, you do not include it in the rate law. Okay, what happens if, so in all of the examples we've seen so far, the concentration has doubled. Well, what if the concentration of one of the reactants triples? Well, then, so it goes from like 0.00100 in trial 1, and then in experiment 2, it goes to this. And then you go, okay, well, sorry, extra 0 there. Well, it goes up by a factor of 3. And then you look at the rate. What's the rate doing? Well, the rate goes up by a factor of 9, let's say. Okay, well then again, 3 raised to what power equals 9, and don't say 3. It's not 3 times 3. It's 3 raised to what power? Okay, it's always about the power, the exponent, to determine the order. Okay, and obviously it's not 3 to the third power, it's 3 squared, and so therefore that would be a second order reaction. Okay, so that's always a safe way to figure out, am I calculating the order correctly? Now, usually these orders are positive integers. Usually it's 0 order, first order, second order, maybe even third order, but they don't have to be. Okay, orders can be fractional. For example, if the concentration of the reactants double and the rate only increases by 1.41, which is the square root of 2, then it's 2 raised to what power equals 1.41. I've only seen that on the AP test one time. And it hasn't been on there in years, but it was probably back in 2012-ish, somewhere around there. Okay? So, but that is technically a possibility. Now, the way you can figure that out is you can use the log function on your calculator. And believe me, guys, I'm no math expert, okay? So if you get those two values, if you go, okay, the concentration of the reactant is going up by a factor of 2, but the rate's actually only going up by 0.5, so then it's actually going down, right? Anytime you're going down by half, 2 raised to what power equals 0.5? I don't know. Well, one thing I do know that I do remember from my early days of math is that when you take the log of something, it removes the exponent. So notice that when I take the log of 2 to the power of x, we get x times the log of 2 is equal to the log of 0.5. And then again, this is certainly a calculator question. And then to solve for x, obviously we just divide both sides by the log of 2, and then we get -1 as our answer. Okay, so on the AP test, almost guaranteed that the the order of each reactant is going to be 0, 1, 2, maybe even 3. Is there a very, very slight chance that it could be some random number like the square root of 2 or a -1? Yes, and that's where you would want to use that log function. But even so, very, very rare. Okay? So let's do one more example and then we'll stop. Okay? So 4 different trials are run for the following reaction, represented by the following balanced equation and data. So here we have 3 reactants. So here we have to be even more careful. A student claims that the order with respect to each reactant is first order. Do you agree or disagree? So we have to look at all of them. And again, we want to find the experiment, like if we start with BrO3-, where it does something, but then the other 2 stay the same. And that's not always trials 1 and 2. Sometimes you have to look around a little bit. But looking at trials 1 and 2, what does BrO3- do? It doubles. So it goes up by a factor of 2. The other 2 stay the same. And the rate also goes up by a factor of 2. Therefore, it's first order. Okay? So with BrO3-, yes, we agree. But it has to be all 3 of them. The order with respect to each reactant. Okay, so we're good on BrO3-. Now let's go to Br-. Okay, that one, you can see it's doubling, and then the other 2 are staying the same. And then once again, just comparing those 2 experiments, yes, Br- goes up by a factor of 2. So does the rate. Absolutely yes, also first order. Okay, and now let's look at H+. Okay, stays the same, again, doubles, but then the rate doesn't double. The rate goes up by a factor of 4. So now it's a 2 raised to what power equals 4, not 1. Okay, that's 2. Okay, so H+ has to be second order. So therefore, what are you going to say? You're going to say, I disagree. Okay, and why? I'm going to justify my answer because H+ is second order, and I'm going to explain why. Because in trials 3 and 4, BrO3- and Br- stay the same, and then the concentration of H+ goes up by a factor of 2. Rate goes up by a factor of 4, meaning that H+ is absolutely second order. Okay, so now when we write the overall rate law for the reaction, we're going to say rate is equal to, don't forget that rate constant, okay? We're going to get into that in our next video. Rate equals K times the concentration of BrO3- first order, Br- also first order, and then H+, and that is second order. And then C, what is the overall order of the reaction? First, and second makes it a fourth order reaction overall. Okay, and we will stop there for today.